Okay, so what about an easier way to do that? Well, we can use the sorted command, which I will show you right here. So suppose I have a, um, let's go ahead and pull up Python and not add it to Bash. Boo, did not add it to Bash. Whatever. Okay, that's fine. I can use it right over here. So suppose I have a list. L is equal to, well, let's say 1, 5, 2, -1, 3. I can do sorted L, and let's see what that description of that function was. Returns a new list containing all the items from the iterable in ascending order. What is an iterable? An iterable is anything you can iterate through. Well, what does that mean? Thanks for the self-reflecting definition there. But the what that means is essentially anything that we can use a for loop over, we can sort, or we can toss it into this. So we'll sort it, and then notice that printing L will give us the same. Well, let's see what happens when we print L. Did say that we'd get a new list, so yep. So sorted L, that produces a new list. So we have to save it. New list is equal to sorted L, and then L. And then we don't want to print L. We want to print new list. -1, 1, 2, 3, 5. Right. Also works for strings, by the way. Let's go ahead and try this. Print sorted spam and eggs. Hopefully this doesn't come out anything too horrible. Space AAD, so it sorted all the letters alphabetically and put them into a list. So that is what sorted does. So how does this help us? Well, we have this list of birthdays and this obnoxious function. But what we're doing is that we're trying to see if two things are the same, and they're a bunch of numbers. So if we sort a list, then any numbers that are the same will end up right next to each other, which is a heck of a lot easier to check. So let's do that instead. So sorted, so let's go ahead and say sorted list is equal to sorted birthdays, right? Because remember, this isn't going to change the original list. This creates a new list. So now let's go through this. For I in range length of sorted list. So again, we're going to go through on this. And what we're going to do is, again, we're using we've seen some for loop patterns here. And this is one that we keep seeing a lot, which is basically I'm going to be going and looking at the next thing in the list. So I'm going to be looking at both the current spot I'm at as well as the next spot. So what does that entail? That entails basically using I+1 to be able to look. If I is this spot, then I+1 is the spot to the right. And I+1 respectively would be the spot to the left. We just don't use that too often. So if I'm going to be looking at I+1, when I get to the end, I want to make sure that that is a valid index that I can check. So I stop one before getting to the end. So I do -1 over there. So for I in range, if this is equal to sorted list I, next is equal to sorted list I+1. This, let's call it after. Or we can just do Actually, we can just do a comparison, make it shorter. If sorted list is equal to, if sorted list at I is equal to sorted list at I plus 1, return true, we've got a match. Otherwise, we're going to go through the entire thing and then return false. It's very important, by the way. I'm going to keep mentioning this. Very important you do not do this. Why? Because if you did this, where we run this, basically this would make the determination on the first line and on the first line only. A lot of students feel like because you have an if, you have to have an else. You don't need to have an else, right? Because what this would do, we'd start index 0. If index 0 is equal to index 1, great. I'd be returning true. But if it's not, I'd be immediately returning false. And when you return false, you stop, which means we wouldn't check 1 against 2, 2 against 3, or 3 against 4, or 4 against 5, which becomes a bit of an issue. Okay. So let's go ahead and basically, when we run this, I'm going to go ahead and print both birthdays as a test, and then print sorted list, and you're going to and you might accuse me of hackery or something. So first, let's go ahead and gen birthday list, and let's generate a list of, say 50 people. And then that'll be our list of birthdays. bdays is equal to gen birthday list, and now has match bdays. Now let's go ahead and print that out. True. It says there's true. So, looks like we have a match at 186 and 186, as well as a match on 132 and 132. Now, when you look at it like this, it doesn't seem like there would be a match, but there is. In fact, I'd put hard money on the next one that there would be a match too. Say like $50, and I'd win that bet. Should I go for double or nothing? I feel like my luck is pretty good. What? You might be saying, how am I getting true all the time? Is there something broken in this? No, there's not. 365 days a year. But it turns out you don't need too many people. Let's start at the top, where I mentioned the magic words, the Pigeonhole Principle. So let's see where this match was. $254. That was the match, 254. So the Pigeonhole Principle basically says, hey, if you've got n holes for pigeons to go into, n homes for pigeons, little boxes for pigeons, if you got n boxes to put the pigeons in, and you've got n plus 1 pigeons, then just by the virtue of just logic, you're gonna have to have 2 pigeons share a spot. So, and if we apply this to humans and birthdays, we can see that basically if you have 365 humans, if you have 366 humans, and if we're excluding leap years, then if you've got 365 humans, then you've got a pair that's guaranteed to have a birthday because you're going to have a repeat somewhere, right? If you've got 1 to 365, got people randomly generated, you're going to have a repeat somewhere. So what's interesting about this paradox is that how often, I was saying I had pretty good odds on this, and I know this because you should never bet against a teacher with a math degree. And at 70, sorry, no, we're not even up to 70 yet. I've got 50 people. So if I've got 50 people, what are the odds that they have a matching, have a birthday? Well, let's actually calculate this by running this a whole bunch of times. Okay, was I so confident about putting hard money down on there being a match? For I is in range. Let's do 100,000 simulations. Okay? So we're going to generate 100,000 unique lists of birthdays. And because printing this would be a mess, I'm commenting out the printing part. And all I'll do is just if has match birthdays. So let's make this, by the way, we should make, when we're doing this scientifically, we should probably do something like this. Trials is equal to 100,000. By the way, when I do something in all caps, which is something you haven't seen me do before, when I do something in all caps like this when coding, this is kind of signifying it's important. In other programming languages, you use this for final variables, which are variables that, once they get set, cannot change. It is the final value. And so in Python, we don't really have that, but we can kind of signify to the user, please do not change this value. Or the programmer, don't change this value, it's important. So for blank in trial, because we don't care about what the variable is, for blank in range trials, so 100,000 times, we're going to generate a random list of 50 birthdays. And if they have a match, awesome. I will simply say count is equal to, I'll have something called matches is equal to 0. And matches plus equals 1 every time I get a match. And then when I'm done, all I have to do is print the number of matches I got, and then I'll normalize it. Well, I'll make it a percentage rather. Matches divided by trials. Now you run this, and it's chugging along. Let's see how long it takes. I am running a video game in the background. Oh, there we go. 97% chance, according to this, approximately. I mean, I could have gotten lucky, but that's the nice thing about doing 100,000 trials. You know, it is ostensibly possible that basically that was rigged like that, but and I got very lucky. But consistent trials, you know, the more you do this, the more accurate you're going to get. So this is a basic Monte Carlo method, which is basically saying, hey, I don't know what the odds are for this. And if you're curious, here's Wikipedia on that page. And it's got a nice big statistical lineup, and says, notice that once you get to above 50 people, it's above that 90% range. In fact, to get to the probability of having a pair, it's 23 people. That's all you need to have a pair. And that seems counterintuitive, which is why it's called the birthday paradox. But that's probably because you're viewing it from a very egocentric standpoint, which is granted, we're very egocentric people. The idea here is that you might be thinking, well, there's 23 people, you know, there's 50 people, just me. If I'm comparing myself to 50 other people, then that's 50 out of 365 chance. But it's not just you, it's everybody else. It's every other pair we're checking, right? Remember that nested for loop? It wasn't just one for loop or another. When I did it like this, I was just simply making it simpler for us to see if there was a match. So now let's go ahead and confirm our results. I'm going to go down to 10,000 to make it go faster. And let's see how it works on 23. 50 point. So we're getting approximately 50% of the time. Statistically, you know, notice that that basically it's 50 here, 49 and some change over here, 51 over here, 51 and a half over here. You know, I'm pretty close to 50. And I'm not really doing any math, right? I'm just in 10,000 trials, my computer spits that out. Like, it's nobody's business. 100,000, that takes 10 times as long, which is not really that long, but it gets more consistent the more trials you get, because luck stops being as much of a factor. Like if I go down to 10, I got unlucky quite a bit of the time there. you know. And here I'm getting 5 pretty consistently, but 6 over there, right? So the more trials you do, right, it's essentially the more significant, the more accurate your things are going to be. And the point is with a Monte Carlo method is that if you really care about it, you can just kind of keep adding zeros until you can say, yeah, well, I could have been lucky, but I'm pretty sure it's this. That's kind of the beauty of this. If you aren't sure about what's going to happen, we're going to simulate these things. So here's the plan for. So this is going on for a bit. So here's the plans for what we're going to do. We're going to enhance this a bit. We're going to extend this, saying, what's the chances of me getting trios? And how in the world do I keep track of that? Because there's other ways we can keep track of. We can do the has match. Then we're going to talk a bit about boring arcane stuff, which is like passing variables around. And then in the following videos, which if they're not up tonight, they will be up. They'll be up tomorrow. As you can see over here, it's quite late. I plan on doing this for character generation for Dungeons and Dragons, for those of you who are fans of that, and for those of you who are fans of more traditional games, blackjack, and figuring out hands and probabilities of strategies in blackjack. So this is kind of an application we can see. Why those things? Because Dungeons & Dragons uses dice, which are very easily simulate, and blackjack, while it uses cards, the rules are very well analyzed and are very, very, very easy to understand compared to other games, as well as very, very easy to simulate. Also, it is like one of the few games that if you actually memorize the correct strategies and employ strategies, that the player actually can have an advantage over the house, which is astounding.